With the physics concepts we've covered so far, we're now in a position to discuss something really amazing, a way to predict the future. The motion future that will work for a wide variety of real-world problems. And it all starts with the first fundamental principle we've just introduced, Newton's second law. Before we start, it's worthwhile reminding ourselves how Newton's second law bridges very different information. It tells us how to take physical quantities we can obtain just by watching the system move during some time interval. Combine that with some knowledge of the properties of our system and connect that to something very different, a measure of the total impact of the surroundings on the motion we're studying, the total interactions of the surroundings with our system. Let's now take this fundamental principle and rearrange it slightly to reveal a way to predict the motion future of our system. We begin by doing a little bit of algebra on Newton's second law. Let's multiply both sides by the time interval delta t. When we simplify, we obtain this result. Now let's recall the symbol delta v stands for the difference in the velocity of the system at two different times. Let's call the velocity at the later time the final velocity, written as v with a subscript f, or v sub f, and the velocity at the earlier time, the initial velocity, written as v sub I. With a little more algebra, we end up with Newton's second law in a form that predicts the future, predicts the final velocity of our system. Let's explore this a bit. Let's imagine that now, at the current time, we want to predict what the velocity will be a little time interval delta t later. On the left-hand side, we're predicting how fast the object moves and in what direction it moves at some later time. But we don't get something for nothing. The right-hand side tells us what we need right now for the current time to make this prediction for a later time. For starters, we need to know, for the current time, how fast and in what direction the object is moving. This is known as an initial condition. We also see we need one property of the system, its mass. Next, we need to decide how far into the future we're going to predict. This is set by our choice of delta t. To make good predictions, we'll typically need to choose delta t small. One way to think about how small is small enough is to look at the final quantity we need for making predictions. We need a good estimate of the net force, the total pushes and pulls from the surroundings acting on our system during the time interval delta t. That is, between now, the current time, and the time when we want to predict the new velocity, v sub f. Our predictions will be good if we choose delta t such that the net force doesn't change much during the time interval delta t. There's a lot more to say about choosing delta t small. We'll revisit this as we need to when we come across specific cases. So we now have a way to predict the object's new velocity, but that's not all we need to predict the future translational motion. We also need to predict where the object will be. We need to predict the object's position. To do this, let's start by recalling our definition for the average velocity. The average velocity is the displacement divided by the change in time. Again, we do a bit of algebra, multiplying both sides by delta t and simplifying a bit to obtain an expression for the displacement, which is the change in the object's position meaning the object's final position, r sub f, minus the object's initial position, r sub I. With just a bit more algebra, we obtain a result that allows us to predict the location of the object, r sub f, a little bit later, a time delta t into the future. Once again, we don't get something for nothing. On the right-hand side is what we need to know to make this prediction. For starters, we need to know, for the current time, where the object is located. That is, r sub I, the initial position. This is another initial condition. Moreover, we also need to specify how far into the future we're going to predict. We need to make the same choice of a time interval delta t that we made for predicting a new velocity. Again, to make good predictions, we will typically need to choose delta t small. Speaking of the velocity, that's the last thing we need to predict the new position, an estimate for the average velocity. We can estimate that from the velocities in Newton's second law. One possible choice is to make an approximation that v average is equal to v sub f. Other choices are possible, and we'll discuss these in context later. But the bottom line is, as long as we choose delta t small enough, our approximation here for v average will work pretty well in many cases. So let's collect all these results together here and quickly summarize. To predict the motion a small time delta t into the future, we start with the initial conditions at the current time, determine the total pushes and pulls now acting on our system of mass m, use this information to predict the new velocity, and then use that to predict the new position. That's good as far as it goes, but what if we want to predict still further into the future? How would we do that? Well, we could do this. Take our new predicted position and predicted velocity and go back to the top where we could now treat these quantities as new initial conditions, a new initial position and new initial velocity. Apply our fundamental principle again to predict one more small time step delta t into the future, a still newer final velocity, and from that, a still newer initial position, which is a prediction of the motion that is 2 times delta t into the future when compared with our original starting point. Now this only works if, and this is a big if, we can determine now what the total forces are for this second trip through Newton's second law. The net force could have changed from the first time we applied Newton's second law, so we would need to allow for a possibly new total net force to make this work. Often we can manage this, so our prediction the second time through will be good too. Now, if we want to keep predicting still further into the future, just repeat the process again, and again, and again, for pretty much as long as we like. We call this repeated application of Newton's second law, iteration of Newton's second law. And so, this is how we can think of predicting the motion for a long time into the future, not as something we do in one fell swoop, but as the accumulation of a large number of small predictions, where each prediction is made for only a small time interval delta t into the future. This procedure is some very powerful motion prediction magic. We will see that we will be able to apply this approach to make predictions in some really challenging problems. To do this may require us to iterate, to repeatedly do this calculation thousands or tens of thousands of times. If you tried to do this all by hand, then forget about it. It would be way too much work. However, computers are perfectly capable of doing this calculation repeatedly, thousands or tens of thousands of times in a snap without breaking a sweat. So that's why we're going to learn to instruct a computer to do this kind of calculation for us. We now know enough motion physics to jump right in and tackle a real-world case that each of us can observe easily in our everyday surroundings. The case where we see an object moving in the same direction at the same speed. The case we will call constant velocity motion. We'll start with examining an example of such motion recorded on video. That's the subject of our next lecture.